I now have the pleasure of introducing Professor Andrew Fabian of the University of Cambridge, who was the 2020 laureate for his great achievements in X-ray astronomy. In X-ray astronomy, you see the violent and hot universe, not only the rather serene universe we see quite a lot in the optical. Please, Andy.
Okay, well, I'm going to give you some idea of the kind of work I do, or have been carrying out over my career. I've had a fabulous time. Astronomy is really exciting, and it's something that makes me want to go to work every day. And my title there is Luminous Accreting Black Holes and AGN Feedback, but a simpler title would be just Black Holes at Work. I'm going to start off, in case there are people here who don't really know what a black hole is, by giving you a basic introduction. The idea of black holes has been around for over 240 years, from John Mitchell in 1783. He was a remarkable man. Indeed, it's difficult to think of physical scientists, people who work in physics, in the 1700s, and he was one of the outstanding ones, although he was trained in Cambridge. He went to Queen's College, Cambridge, but he spent his career as a rector. That means he's a vicar, if you like, of a church near Leeds. And that's where he did his work, including this. And he worked on gravity. Bear in mind that Newton, 100 and something years earlier, had actually come up with his theory of gravitation. And he came up with, he was starting to think about can we measure the mass of stars? And he was thinking, well, light consists of particles. That's what Newton had told us that light is. We now know it's both a wave and a particle, but if there are lots of particles being emitted by a star, then gravity is going to act on them. And so therefore, if I can work out how they're slowed down by the gravity of the star, I'll be able to measure the mass of the star. It doesn't work like that, because light always travels at the speed of light. But anyway, he got the right answer from this trivial argument. He knew the sun's escape velocity is 600 kilometers per second, and he knew that the velocity of light is 300,000 kilometers per second. That had been worked out in the previous century by a Danish astronomer, Rømer. So he knew what the velocity of light was, he knew about the sun's escape velocity, and he realized if he packed 100 million suns together, stacked them together, don't ask how you do that, but imagine you could, then the escape velocity from that, according to Newton's law, would be equal to the velocity of light. Therefore, it would be black. Okay, we could not see it. And so the question is, how could we see such an object? Now, we're going to see that dramatically this afternoon in Jeff's talk, but basically he came up with the right answer. You see how it influences surrounding gas and stars by its gravity. So what you're looking for, if you're going to look for a black hole, is gas or stars which are being swirled around. They've got a large velocity, indicating there's a large gravitational field acting on them, but you can't see anything right at the center. So that's a black hole. They're regions of space where matter has collapsed inwards, and matter can go into them, nothing can come out, at least in our universe. The next step was Albert Einstein. This is a letter from Zurich in 1913, where what he's doing is writing to somebody about, that's the sun, there's a light beam coming along here, it's being bent by the gravity of the sun, and he's got the angle by which it's being bent by as 0.84 arc seconds. That is the wrong answer. Einstein got it wrong by a factor of 2. You have to consider both space and time, as he went on to tell us, and by 2015 he'd come out with his general theory of relativity, which actually explains everything. But actually he thought at the time that there weren't any solutions. He didn't know of any solutions to it. That came the next year from Carl Schwarzschild. Carl Schwarzschild is here, and he came up with a solution which we now call the Schwarzschild black hole. And it was the concept of the black hole, although there were various things, misunderstandings about that at the time, and people didn't really think much about black holes as being possible objects in the universe. But this was the solution. He unfortunately died the following year, the same year he came out with his work. And some of us older astronomers will have met Martin Schwarzio, who was his son. And I remember Martin Schwarzio in the 70s was the last person I heard who gave us a detailed astronomical lecture, which we all followed, but he had no visual aids whatsoever. He didn't even write on the blackboard. He just talked to us for an hour. And that's very unusual, but that's how some lectures used to be back then. We have to wait nearly another 50 years before this man, a New Zealander, Roy Kerr, found the solution to the spinning black hole, the rotating black hole. Black holes can only have mass and spin. They can possibly have charge, but actually we don't think that charged black holes exist in our universe because the interstellar space is conductive, which would sort of short them out. So forget about spin. They only have mass and forget about charge. They only have mass and spin. And it was his equation. Initially, again, people didn't think he got the solution, but it took a while before people realized that Roy Kerr actually had the solution to spin of black holes. And I took that picture of him in his place in New Zealand. The size of the Schwarzio black hole is 3 kilometers per solar mass. The equation is 2gm over c squared, which is very simple, and is exactly the same solution that John Mitchell had. John Mitchell was going at it, and we now know that that's inconsistent and wrong, blah, 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 but it comes up with the same answer. So it's the one I remember. Roy Kerr showed that if you have a very, very rapidly spinning black hole, it reduces to gm over c squared. But that is, and I believe that if a civilization is still around 1,000 years from now, and there are astronomers, they will talk about Kerr black holes. This is the one that is the general solution. Then coming into when I was at school, 1962 to 1963, this is when things changed in astronomy. Up until then, there were a few papers on black holes and the like, but they were amongst by mathematicians who nothing to do with observations, no real concept that black holes might be out there. And it starts with the first successful X-ray astronomy flight by Riccardo Giacconi. And this was a sounding rocket flight where you launch a rocket with a detector, an X-ray detector on the end, which is rather like a Geiger counter, and it went up and it spends like 10 to 15 minutes above the atmosphere looking at X-rays from the sky. X-rays are absorbed by light, by matter, and the kind of X-rays we look at, if we had them in this room, they would only travel about that far. So clearly, you're not going to be able to look at the night sky from the ground. You've got to go in space. So Riccardo did the first flight, opened the subject up, and he got a Nobel Prize back in 2001 for that work, coupled with his later work from the Uhuru satellite of seeing Cygnus X1, the first stellar mass black hole that we think is around. Then, just in the same 12 months, 3C273 was discovered to be highly luminous by Martin Schmidt. I say discovered to be highly luminous. It was discovered as a radio source. It's the 273rd object in the 3rd Cambridge catalogue of radio sources. And the position of it was established by lunar occultation measurements by Cyril Hazard in Australia. The positions went to Palomar Observatory, where Martin Schmidt did his work, and he looked and obtained a spectrum of 3C273, a sort of color, splitting the light out from 3C273 according to its color, and it had these bands in, emission lines, which he didn't understand. And then suddenly, after a couple of weeks, he realized he was looking at the spectrum of hydrogen, redshifted by 16%. That means it's very distant, and therefore has to be very luminous, because you can see 3C273 in quite a small telescope. So very luminous. And then later in that year, there was Roy Kerr came out with his metric of the spinning black hole. And so this was the start of relativistic astrophysics, which is what I do. And how this works is through the accretion disk. That's how the matter swirls into the black hole. As matter falls into a black hole, it's accelerated by gravity of the black hole. It swirls round it, and it reaches a velocity of half the speed of light. If there's any friction in this disk, then that leads to an enormous amount of gravitational energy release, which is why these objects are so luminous. And Donald Lindell was the first person to write down how that might work. There is Martin Schmidt, Donald Lindell, and Fred Kavli there, and they were the first astrophysics laureates of the Kavli Prize. So that's coupling everything together. So this is Cygnus X1, a stellar mass black hole in orbit around a giant star, a B supergiant star, and you can see it in binoculars if you know where to look in the constellation of Cygnus. But you can't see any of that with the naked eye or with the binoculars or anything. But if you have an X-ray telescope, even a modest X-ray telescope, then you can pick out the X-rays that are liberated by matter, which is the gravity of this 20 solar masses, 20 times the mass of the sun black hole, is dragging matter off this 20 solar mass supergiant star. That's represented by this artist's impression of this material comes down and joins in this disk here. That's where it joins the disk, is given a little bright spot there, and swirls down like that, liberating its energy, becoming extremely luminous, okay, at the center. And sometimes there are jets squirted out of these things, which we don't fully understand, but let's carry on. So this is Cygnus X1, a black hole in our galaxy. There are millions of them in our galaxy dotted around, and right at the center of our galaxy is one large black hole, 4 million solar masses, that you're going to hear about this afternoon. You're going to see this afternoon. I'm not going to say how you can see it, though. They don't really see it, but they see stuff around it. Because it's right in the center of our galaxy. This is a Milky Way here. That's looking in the constellation of Sagittarius. You look right in there, and if you could get rid of all this dust in the Milky Way and look through, they have ways of doing that, you can see right at the center is the black hole. This is 3C273. It's extremely luminous, and it does have a jet. There it is. This is a picture from Hubble, of course. The cross like that is the diffraction spike from the telescope. The support structure of the telescope causes these diffraction spikes, and that's a star in our galaxy. Okay, that star is probably, I'm going to guess, roughly the luminosity of our sun. It's probably a bit more luminous, okay? It's probably a kiloparsec away, that's a gigaparsec away. This is 1 million times further away than that. And from the inverse square law, this is therefore 1 trillion times more luminous than that. That means the amount of energy per second that comes out of this thing is 1 trillion times the luminosity of the sun. Actually, I'm understating, it's 10 trillion, okay? And what they found within the first year of the discovery of 3C273 back in 1963 is they looked at past plates of this object, and you can see it. People 100 years ago had pictures of this object. They didn't know what it was. What they found was it varied in brightness. So it's something that's 10 trillion times the luminosity of the sun that varies on a timescale of a week. If it varies on a timescale of a week, it's got to be smaller than a light week across. So it's smaller than the total extent of our solar system. So something solar system sized is giving out 10 trillion times the luminosity of the sun. At the middle of it, there must be something special. Yes, it's 1 billion solar mass black hole. It's sucking material in, and the gravitational energy release of that falling in is given out, and it's what makes it so luminous. So it's that kind of thing that captured me that long ago, 50 years ago, so more, and I want to study these, I want to understand them. Now, what I did for my thesis was I was tasked to measure the granularity of the X-ray background. what was discovered by Riccardo Gicconi with this rocket flight was a very bright source in the sky, X-ray sky, called SCO-X1, but also there was background radiation of X-rays. And I was to study that and see if it was granular, if it's due to individual sources. I provided the first limit on its granularity, but this is what it looks like in a modern X-ray telescope, so-called XMM, and all of these individual objects are separate objects and blobs, and basically, this is the X-ray background, the sum of all of those, and 95% of these dots are accreting black holes in other galaxies. Each of them is one in a distant galaxy where matter's falling into a black hole. And the fuzzy objects you can see are clusters of galaxies, and I'll end talking about clusters of galaxies. So this was my thesis, my first rocket for my thesis. Skylark 1001 going up from Woomera in Australia. Woomera is Aboriginal for throwing stick. Okay, they used to throw a spear by having a throwing stick, give them a much greater lever arm. So this thing thundered up into the sky back in January of 1971. I was in a bunker just off from here, and as it went out of I couldn't see it. I was looking at the data from my experimental, my proportional counter was being transmitted down onto a little TV screen, and I was watching it, and as it thundered up the rails and out of the launch site, basically my signal went blur and disappeared, and I thought, I won't say what I said, but but you can imagine what I thought. And then another guy just came over and turned a switch, because I was tuned into an aerial that was in here, inside this metal tower, so consequently it couldn't detect this once this was out here, and they were tracking it with them, and suddenly the signal came back, and there it was, hooray, fantastic. And so I did get all my data back, but I had to go out into the desert to recover the radioactive source the next day. And what goes up must come down. And here's my detector down here. There's another part of it, and that's me going back to the helicopter. And I spent all that day in the helicopter, and I'd never been in a helicopter before, but it was quite exciting for the first 5 minutes. But going across the Australian desert in January, when it's extremely hot and they have salt pans and so forth. And so the helicopter will go across like this and then suddenly go up like a lift and then come down again. By the end of that, I didn't want to go in another helicopter. So back to 3C273 and on to, I've tipped everything round. I talked about how it has a jet sticking out there like that. In the center of 3C273, there's this swirling disk of gas, and maybe this jet coming out the side like this. And I've tipped it back round like this into this schematic. And this is the kind of thing that I've been working on is in the X-rays. What we see is a emission directly from what we call the hot electron corona. There are lots of very hot 100 keV electrons up here that scatter photons, and that goes to the observer. It also irradiates the accretion disk. So it's like that, and this light here, you've got to imagine this being 1 trillion times brighter than the sun, but you can't paint that or do that. So it's irradiating this disk. So we see light coming back from the disk, and we call that the reflection spectrum. And that's something that I worked on for a long time. There's the reflection spectrum. And with Randy Ross and now with Javier Garcia, we're able to make or predict what the spectrum should be like. And this is where we've dragged this out, so we're showing the light, that what we get back, what the spectrum should look like as a function of X-ray energy, and that's measured in keV for the non-scientists amongst you. Don't worry about that. But what we see is the ionization parameters proportional to the flux over the density of the surface, and when the flux is modest, then you get these strong emission lines, and as you go up, increase the flux, so the emission lines sort of start to go away. But if you've got that kind of thing, what it means is we are looking at atomic transitions in the accretion disk. we're able to look at atomic transitions from around the black hole, which is giving us, as though there are lots of little clocks going around the black hole. This is just atoms, and this one here is due to iron, so it's electrons jumping up and down inside ions. And by looking at that, we can tell where we are relative to the black hole. It works like this. So this is now broadening the line. This is the accretion disk. And this is a spectrum where the frequency or energy of the photons goes to the right. And if we're in Newtonian mechanics, we expect a double-horned line from this. And indeed, that's quite common to see in astronomy from disks around stars and the like. But then, if you're going around a black hole, it's going up to half the speed of light. We have to include the transverse Doppler shift and also beaming. When something is going close to the speed of light, it's moving towards you, it's beaming brighter, so the blue side is brighter than the red side. And then we're around the black hole, so we've got gravitational redshift. And when you add all these things together, you get a skewed line like this. And so the line emission should look like this. It should be skewed like this. And if it's a Schwarzio black hole, it'll have roughly this shape. And if it's a Kerr black hole, in other words, a spinning black hole, a rapidly spinning black hole, it'll look like that. And I, with others, Luigi Stella was the one who actually plotted these curves, back in 1989 came out with, this is what we should be looking for. And so I tried to persuade people to have a go at doing this. One thing, before I go further, is the Schwarzio black hole, which is non-spinning. You notice it comes down here. This side is roughly the same, but coming down here, the Kerr black hole, the spinning one, goes even further. That's because it has a larger redshift, so you can, by measuring that, you can tell the black hole spin. And many of us, including my colleague Chris Reynolds, has been doing that over the years, and we find this is a measure of black hole spin. We can find that many of those ones that we've measured have got high spin. There's a sort of catch here because of the fact that these are the ones we've measured, and it's actually easiest to measure them if they've got high spin. So we don't know what the full picture is. But the first broad line was found with the ASCA satellite, which is a Japanese-US satellite, back in 1995. This is the data. It looks pretty ratty, but we were really excited by this. But you can see it's got this broad line emission. And here am I, my wife Carolyn, and this is Yashua Tanaka, who was the PI of ASCA, and I collaborated with the Japanese for many years, and so this was how we broke through and found the broad iron line. And some of you who know astronomy know these two fellows as well, and maybe these. So I just want to show that we've got many of these now using Fiona Harrison's new star. We can look at the spectrum. This is what the spectrum sort of looks like, unblurred. That's the jiggly line. And then when you blur it, it gets smoothed out and shifted to the red. And we're going to look in this energy band. We're looking for the broad iron line and the so-called Compton hump. And this is what it looks like in the data. These are lots of active galactic nuclei, which are sort of mini quasars. There you can see this broad line and then this Compton hump. This is Cygnus X1 that Riccardo Giacconi discovered in 1962, and it's got a similar broad line and Compton hump. So one of the things about black holes is they only have mass and spin. So you can look at a 20 solar mass black hole, and this one is going to be a million solar mass black hole, these ones, and this one is more like a 100 million solar mass black hole. They all have the same spectra, okay? And here's a nice one that one of my students did. He's not a student anymore, but Mark Erin 335, just to show you what we can see sometimes. The data are the little data points here. The unblurred emission is the blue line, okay? And the blurred emission is when you blur it, you get the red line. And it turns out there is a line, part of the line here that's not shifted, so it looks like this. And so therefore, you can see there's this enormous redshift. That is the redshift of material very close to the black hole, and most of this emission, therefore, is within 3 gravitational radii, 3 gm over c squared. So we're looking at stuff which is very close to the black hole. And this is one beautiful one. Another of my students measured a couple of years, 6 years ago now, where you can see it's very clear, lots of data, lots of high-quality data. I'm now going to go into this part of the spectrum and on from there, and we're going to just notice, looking at an active galactic nucleus spectrum, is on this, that there's absorption here. And this is just one extra little wrinkle that I've been working on recently, is that the absorption either represents a very fast outflowing wind, or it could come from the disk. And if it's the disk, I think it's more exciting, although most people think it's an outflowing wind. I mean, I don't mind being controversial, and indeed, I'm the sort of person who Monday, Tuesday, Wednesday, I'll think it's this. The rest of the week, I think it's that, and I don't mind, okay? Be a scientist, you have to have 2 solutions in your mind at once. And it's possible above the disk there can be absorber, and this is what it would look like if you were to look at this object. There's, and you'll see in Jeff Bauer's talks, lots of pictures like this, but this is a computer simulation. The black hole is here. This is the side of the disk coming towards us. It's very much brighter than the side going away because of special relativistic aberration. And it's also blue shifted here. This is a blue shifted, that's red shifted. Oh, it's done something there. And here, and here, wow, good. Anyway, you know what computers are like. Here we are, 2022, and they still haven't fixed this problem. Okay, but this, anyway, these are contours in shift of energy over emission, and it sort of works. That's all I can tell you. I'll move on from there. Another aspect of this is that variability of the power law seen directly and variability seen in the reflection is going to be different because there's going to be reverberation, like an echo. This room is starting to echo, but you've got the 2 different path lengths of the light. This will lag behind that. And I won't dwell on this, but this was first discovered in this object. We published it in 2009. The reverberation was spotted by Phil Utley, and it's in this diagram. Erin will talk about this kind of thing later, and this is a 30-second lag between the 2. So there's a lag of 30 seconds, and that sort of, for me, clinches that the picture I've discussed is likely to be right. Erin's work went on looking at many objects, and this is part way, this is 6 years ago. She's going to take you up to 2022, and you can see that the lag amplitude fits in terms of radii between 1 and 10 gravitational radii, so you're very close to the black hole, and these are many objects. You have to do some more interpretation to this diagram to come out with precise numbers. I'll let her do that. Now I just want to talk about the work that black holes do, which is black hole feedback. Just in terms of, I've only got one equation. It's E equals mc squared, which everybody's heard of, okay? And that's coupling energy to rest mass. And so in terms of chemical energy, roughly the energy liberated in chemistry is like 1 part in a million. Okay, so you're sitting there digesting breakfast. Okay, E equals mc, energy's coming from the mass of the food you ate at the level of 1 part in a trillion. So you can ignore that. We couldn't measure the change in mass and so forth. But that's what petrol also does. It's all the same thing. If you go to nuclear fusion, it jumps by an enormous amount, which is why, nuclear bombs have got relatively low mass, and also nuclear material in nuclear reactors is very low mass compared to all the coal and gas we shovel into the other ones. But then black hole accretion is a factor of 20 up on that. Okay, so you liberate 10% of the rest mass energy if you accrete it onto a black hole. It can actually go up to 30%. The 100% would be complete matter-antimatter annihilation, which doesn't happen much in the universe, thankfully, because there's very little antimatter in the universe. And if we look at a black hole, if we've got a billion solar mass black hole, we've got tenth of that, 100 million solar masses times c squared. That's the total energy that's released in actually accreting that matter into the black hole. And that is about 100 times the energy required to either unbind or went into binding, making the host galaxy. So you're liberating an amount of energy which is more than sufficient to blow the whole galaxy to bits. Okay? However, how do you couple the energy liberated by the quasar, like 3C3, which is mostly radiation, and that, how do you couple it? You can't couple it to the stars. You can actually couple it to the gas in the galaxy. So you can actually blow the gas away out of the galaxy. So imagine that kind of thing. Ways of blowing it out. I'm looking at now this wonderful picture of comet Hale-Bopp, which the older ones in the audience will remember from the 90s, brightest comet for a long while. And comets always have a tail pointing away from the sun. This is the dust tail, which is blown away by radiation pressure on dust. This is the wind tail, solar wind blowing it away. Similarly, in quasars, enormous source of radiation and possibly winds. The winds can blow things away. Radiation pressure acting on dust, which is something I've worked on, is also going to blow the matter away. And they are the two different ways in which it works. But what this means is that the black hole at the center of a galaxy can affect the amount of stars in the galaxy, the stellar growth of the galaxy. So the end growth, the end total stellar mass in a galaxy is determined by this sort of process. And this is just a little movie of what might be happening. This was work done with Roberto Mailino, where we observed. And also, as it blows gas out of the galaxy, this is meant to represent stars forming in this outflow. And therefore, you can put stars through the action of the black hole at the center. Stars can appear where they would not have appeared before. So you can change the shape of the galaxy. So all of this is rather exciting and can explain certain things about galaxies. And on to, and the end I'm going to leave, is into clusters of galaxies, where clusters of galaxies have the most massive galaxies in the universe. And they are sitting there. This is the Perseus Cluster. This is a beautiful picture taken with a 30-inch telescope by a guy in New Mexico. And these are big fuzzy galaxies, elliptical galaxies in this cluster. And these ones don't have any star formation. This object is weird, NGC 1275. I'll talk about it a little bit more later. It's the one at the center. It's the most massive one. But if you now shift from this picture to one taken with an X-ray telescope, it looks like this, to exactly the same scale. And what you're seeing is the gas between the galaxies. Most of the gas in the universe lies between galaxies. It's not in galaxies. And in a cluster, that gas is made visible because it's fallen into the potential well of the cluster. It's being squeezed and heated, so it actually has a temperature of 100 million to 1,000 million, 100 million degrees. It radiates X-rays, and that's what we're seeing here. So this is the hot gas there. How do you sort of push gas out of a galaxy when there's all this gas there? Well, what happens is you make bubbles. And these are bubbles blown by the black hole in NGC 1275. That thing there and that thing, and this and that are bubbles that were blown by the black hole at the center. And the scale of this bubbling and the scale of the event horizon of the black hole, that's the size of the black hole, to the size of this bubbling structure is 1 to 10 to the 10, 1 to 10 billion. Okay? And the mass of this object is probably 1 billion solar masses at the middle, but it's sitting there, it's powered by accretion, and it's sending out jets north and south. We can see them in the radio, and they are filling, and the jets come out, can't propagate very far because of this gas that's out here, and so they form bubbles, and so it's bubbling away there like a bit like a fish tank aerator. Okay. And there's the radio emission shown there, sitting in those bubbles. And this is a beautiful picture. I'm the PI of these Chandra observations, although there's an enormous number of people involved in doing this work. I didn't do all this myself, and this picture was not made by me, but I think it's beautiful. And we can see ripples out here, and I think those ripples are sound waves. And so there's a frequency of sound waves. It's 1 to 10 million years. Okay, it's a little slower than the kind of ripples and sound waves that you'll hear about in the next talk. Okay, but what you have to do is think about the universe. Go out one starry night and look at the stars. Each star has its own frequencies. But if you have a small telescope and can look at galaxies and clusters, they have their own frequencies as well. And this is the Hubble Space Telescope image I managed to get of this emission. It's from there to there is roughly 8 times the distance between us and the center of our galaxy. So this is a truly spectacular structure in the sky. I was very interested in how this was powered. I often used to go observing with my wife Carolyn, who looks much chipper than I do. I look as though at 3 in the morning, those of you who do optical observing know what it's like, but there we are. And this is the Centaurus cluster, another cluster, and I think that nucleus is there, and the bubbles are these things. And this is a final Hubble picture of it, which we managed to get about 10 years ago, and looking into the center. My latest paper, I'm not going to describe it, is all to do with what's in there. It's called Hidden Cooling Flows. I think there's a lot hidden here. What you see is, what meets the eye is not everything. And there's much more to do, much more to discover about these objects. And I want to end by just with a summary. Black holes are very common in the universe. They go from stellar mass up to 10 to the 10 billion solar masses. They can become the most luminous, persistent objects in the universe. They measure mass and spin, and they can actually change if, when, and where stars form in a galaxy, and they cause something that was noticed in the 90s, which triggered lots of excitement. The mass of the black hole is 1,000th of the mass of the galaxy, which it looks some way, it looks as though the galaxy should influence the black hole, but that black hole influences the galaxy. And in the most massive ones, we get the bubbles that do the bubbling. And this is just a few of my mentors, collaborators, colleagues, and students. You don't just work by yourself on this kind of thing. Work with lots of students, lots of collaborators, and I could have shown you many more slides like that, which I won't. Thank you very much.